Before delving deep into the details of network slicing, I make some consideration first about the evolution of data traffic and 5G. Data traffic, especially mobile data traffic, has been steadily increasing and is expected to further increase by 2024. This evolution is a result of the continuous improvements of the telecommunication system and subsystem and the optimization of the protocols. Not only that, better networking allowed the development of more complex and useful services, which led to an increased demand of connectivity from the customers. Of course, this increased demand was accompanied by the development of different types of devices with the ability to connect to an internet network. Every customer today owns several of those devices, and this trend is increasing. There has also been a shift in the type of communication itself, that is, the communication has become more sectorized and service-based. To support this data flow growth and the increasing demand for specialized data traffic, such as machine-type communication, the 4G network architecture is no longer efficient nor sufficient because some elements of the network infrastructure, such as legacy mobile networks, have few adjustable parameters, which do not allow for agile scalability. An upgrade of the current global network infrastructure is in order, and that's what 5G is. It's clear that 5G cannot just be about having faster data rates. The goal is to provide better support for mobile broadband applications and services, but also vertical industries, such as automotive systems, smart grid, public safety, Internet of Things, machine to machine. To achieve this automation, programmability, modularity, and network slicing are key ingredients. More and more companies are investing in technological advancements related to 5G, 5GPP, 3GPP, Ericsson, Huawei, Nokia, ZTE. Network slicing consists of exposing a common network infrastructure in the form of different customized logical networks called slices. Each slice is made to support one or more applications and can be operated by a provider other than the owner, and is made by a collection of network function and specific radio access technology settings. A provider can be a mobile virtual network operator for the mobile broadband market, for example. To implement network slicing in mobile networks, we obviously need SDN-enabled control planes, network function virtualization, cloud computing. And the reason why we need this is because, for example, the network function virtualization allows us to use a general purpose processor platform, a cloud operating system, an hypervisor, and a distributed computing. This slicing is not just about technological advancements. It's also a business related subject, and the purpose is to enable rapid business expansion. This is where the concept of network slicing as a service is born, which refers to how operators agilely provide a network as a service to a customer. Agility in this context refers to the ability to deploy a fully functional network virtually, possibly in a matter of minutes, rather than installing that network physically. This network will also have specific quality of service characteristics and will be able to serve a certain number of users across a specific set of networks, according to the relationship between the service providers and the consumers. From a purely business perspective, network slices can be divided in the following categories. Business to business. That is, the operators sell their network slice to a company who owns both the networks and the terminals. Then there is business to consumer, where the operators provide a small network such as a home network to a customer, which can enjoy a slice once they put a SIM card inside a control device. Business to customer, where operators offer dedicated connections to a broker, which engages with the end customers. We can also analyze this from a service perspective and also get some categories on that. We have, for example, industrial slice, that is, the customers with the same network service requirements are registered with the same slice. A monopolized slice, any customers who pay for the slice uses it as a private network. And maybe an event slice. A slice is launched for some events with relatively short life cycles. Of course, being able to offer slices as services come with all sorts of possible enabling capacities. New use cases, new services can stem from this as well, such as the operators can more easily differentiate the data pipes with various quality of service and be able to provide more complex services that is not just voice, SMS, or data. It's also clear that if we have a virtual network in place, the configuration creation of a slice is just a matter of configuring some files. So this configuration needs certain parameters, of course. That is some infrastructure information, that is the IP address, and some data pane information and IP addresses of and VLANs of base stations. Some service information, that is basic LED identifiers and protocol interfaces, some subscription information, and also some slice registration, how to find the slices, monitoring and billing interfaces where the key data and billing files should be sent. The orchestrator can thus instantiate the network slice through assembling functionality of vendors, such as virtual network function and base station selection, and manages service chaining, subscriber management, monitoring, billing. The orchestration is at the infrastructure level is made simpler by the cloud operating system, such as OpenStack, VMware. At the network function level is more difficult to create standardized services for management, session management. Operators can also agilely offer dedicated network services to small and medium enterprises rather than build expensive networks for that. For example, a wine company can deploy a network of sensors in the vineyard that collects information regarding humidity, temperature, intensity of the sun, which are sent to the cloud, where some analytics software using machine learning can analyze all that data and say, for example, when is the best time to harvest the grapes. It's interesting to know that in this case, a slice can be composed of different parties. One vendor can provide device connectivity, management, and security. An operator can provide mobile connectivity. A third company could provide an IoT gateway, and another one the analytics system. But how can network slicing be actually implemented? For example, if you consider mobile broadband, there is only one physical channel, that is the air, and many services with conflicting requirements that will need an appropriate slice of that channel. What is done here to solve this problem is divide logically the physical network. There are some forms of network slicing that have actually been implemented in fixed networks, such as VLAN and VPN. Mobile networks, however, the logical separation is more complex and happens at the access, the transport, the core level. The OSs and BSs are also modified. To achieve this, SDN plays a key role because it allows virtual network functions, connectivity, the modification of the service chain. 3GPP has defined and ratified different kinds of architecture. The first one is the run-only slicing. What is done is divide the base station into logical base station and apply various parameters to the area interfaces to implement slices. Isolation among slices with one key requirement. Traffic isolation refers to a situation where the traffic overload of one tenant does not affect another tenant. This is already implemented in multi-tenant data centers or wired network domains, but is an open research challenge in wireless domains, especially in a multi-cell RAN scenario. Radio-electrical isolation is also important and aims to avoid interference in the area interface. The achievable resource utilization efficiency of a specific resource block depends on the combination of implemented physical layer, if and what type of adaptive modulation is used, and what type of hybrid automatic repeat requests are used, what type of multiple input, multiple output techniques are used, etc., etc. Also the RRM process. Another important aspect that is worth considering is the granularity of slicing. that is the minimum frequency time space that can be assigned to a tenant as a certain level where the slicing is occurring. So as a matter of fact, we can do slicing at different levels. For example, we can do slicing at the spectrum level. Spectrum resources is a RAN infrastructure provider arranged in carriers, and each tenant gets its own set of carriers. A tenant-specific spectrum planning function can decide how the carriers are used across N cells and how the resources are allocated to each radio access bearer. We can analyze the granularity. So the minimum frequency is one carrier, that is 1.4 megahertz in LTE. The minimum time is several minutes, after which the carriers can be reassigned with spectral allocation strategies. We have a high degree of customization because we have, at this level, we can pretty much change the spectrum allocation and the intercell interference techniques and all the other things, basically. And also, because of this, we have the highest degree of radioelectrical isolation. Then we have slicing based on intercell interference coordination function, which is a function that mitigates interference caused when neighbor cells use the same carrier by imposing a set of limitations that in what resource blocks a cell can use. When intercell interference coordination function based slicing is applied, one carrier can be assigned to more tenants, but each slice has its own resource blocks inside that carrier. This is the most basic static implementation, but dynamic versions could also be implemented. After this, each tenant can implement an IC strategy for his resource block when cells are neighboring. The granularity is the minimum frequency is one resource block, that is 180 kilohertz in LTE, and the minimum time is 100 of milliseconds, after which the resource blocks can also be reassigned among tenants. Very good customization and very good isolation, but not as good as the slicing in the frequency domain. Mainly because we are at a lower level, so we have less control. I mean, we cannot access on the frequency here, whereas we could in the previous level. Then there is slicing based on packet scheduling. That is, the packet scheduling function decides for each carrier which resource block can be used for each RAB, and operates at every TTE. In LTE is 1 millisecond. Each individual cell decides independently how to distribute resource blocks among the tenants. The admission control process decides whether the style image request of radio access bearer is accepted or rejected, and acts on the individual cell. After a tenant-specific admission control function decides to admit a radio access bearer request, or the admission control makes the final decision of admitting or rejecting that radio access bearer, considering the situation of all the tenants. These last two ways of slicing, though, don't allow a very good customization or isolation. There is multi-operator core network architecture, where core networks are virtualized as network slices with component-like functionalities that are programmable and auto-configurable, such as mobility management, session management, authentication. Slice selection function is added between the control plane of the core network and the eNode Bs for the selection of the correct slice. Slices are organized in some categories that are extreme mobile broadband, massive machine type communication, ultra reliable, low latency. Orchestrator is proposed on top of a NFV-like architecture, which translates to the slice provider request by selecting the appropriate virtual network function. It is a service graph which specifies how logically everything is connected. Virtual network functions are deployed in the cloud using a virtual infrastructure management, and SDN rules connect them. Each slice has its own SDN controller. The slice orchestrator instantiates the core network elements using a physical network function or a virtual network function. Each core network instance has a set of virtual network function and physical network functions which perform functions such as mobility management, authentication, data plane, forwarding, etc. Core network instances are connected to the eNode B using ES1 interfaces or other type of interfaces. The eNode B is able to steer the slice traffic to the correct core network using slice or tenant ID. that the served UUE communicated at some point in time. The ID also contained information about the slice type. This allows the eNodeB to use the appropriate MAC scheduler. The eNodeB stores a map between the tenant ID and the CN elements. The network slicing enabled eNodeB differ from the LTE eNodeBs because they have a resource mapper which acts as the interface between the resource blocks and the slice resource management. The resource mapper communicates to the slice resource manager the number of packets per UE and per logical channel, the channel quality of each UE, etc. The slice resource manager schedules UEs to virtual resource blocks, mapped to actual resource blocks by a scheduling algorithm such as round robin, every transmission time interval. Doing this optimally is an NP-hard problem, as slice specific policies enforced by the slice orchestrator to the resource manager when a slice is created. An agent takes charge of the communication with the eNodeB controller. For example, the slice orchestrator communicates the policy of a slice and scheduling to the eNodeB controller, which translates this to MAC-related configuration messages to be sent to the eNodeB agent, which will configure the slice resource manager. I conclude by saying that implementation of 5G is still in the initial stages, and so is the implementation of network slicing. Some things that have been discussed in this presentation could change or evolve drastically. But the main point to consider is that network slicing is an enabler for a service-based internet and one of the main pillars of 5G. There is tremendous potential and some interesting results will surely emerge and be seen in the following years. Thank you very much. This was my presentation. Have a good day.